Section 8.3, Probability Applications of Counting Principles. The Environmental Protection Agency is considering inspecting 6 plants for environmental compliance, 3 in Chicago, 2 in LA, and 1 in New York. Due to lack of inspectors, they decided to inspect 2 plants selected at random, 1 this month and 1 next month, with each plant equally as likely to be selected, but no plant selected twice. What is the probability that 1 Chicago plant and 1 LA plant are selected? So, the total number of plant options we have are a combination using 6 plants and choosing 2 of them. Those are the total options we have for picking plants. I'm particularly curious about a Chicago plant and then an LA plant. So for my numerator, the word "and" means that we're going to multiply those probabilities together. So I want to have a combination of 3 Chicago plants, choose 1, times the combination of 2 LA plants, choose 1. So we're going to have to use our rules from last section in order to find the probability of this happening. So remember our combination rules. We'll do the whole thing all at once here. So we'll have 3 factorial over 3 minus 1 factorial, times 2 factorial over 2 minus 1 factorial, all over 6 factorial over 6 minus 2 factorial, 2 factorial. So if we simplify our numerators here, 3 minus 1 is 2 factorial, so we'll have 3 times 2 times 1 over 2 times 1 times 1 times 2 factorial is 2 times 1. 2 minus 1 is 1, so 1 times 1. All over 6 times 5 times 4 times 3 times 2 times 1 over, well, 6 minus 2 is 4, so 4 times 3 times 2 times 1 times 2 times 1. So we're able to simplify a bunch of items here. Let's see what we can simplify. 2 times 1 times 1. The 1's cancel because multiplying and dividing by 1 doesn't change anything. 4 times 3 times 2 times 1. So on the top it looks like we have 6 over 6 times 5 is 30 divided by 6 times 5 is 30 divided by 2 is 15. And 6 over 15 is 2/5. So let's do the same thing, except this time we want 1 New York plant and 1 Chicago plant. So if we look above, we want 1 New York and 1 Chicago. So we have to do the same thing here. So we want New York is, I have 1 option and I get to choose 1 of them. And then the Chicago is still 3. So 3, choose 1 of those plants. And we already figured out what 3 choose 1 is up above. So we can replace 3 choose 1 with simply just 3 because that's what was left over. All over our entire options are 6 choose 2. And we figured that out up above here, and that ended up resulting in 15. So we already know this part here. So this is equal to something over 15 multiplied by 3, since 3 choose 1 is 3. And if we think logically about this, if I have 1 item and I want to choose 1 item from it, we only have 1 choice to choose from. So 1 choose 1 is the same as 1, which is the same as 3 over 15, which is the same as 1/5. But you could, if you don't see that the combination of 1 choose 1 is 1, go ahead and use the formula and plug it in to verify that that works. From a group of 22 nurses, 4 are to be selected to present a list of grievances to management. It doesn't say in any particular order, so we just want to see how many choices we have. So if I have 22 nurses and I choose 4, we'll have to use our rule. So 22 factorial over 22 minus 4 factorial, 4 factorial. 22 minus 4 is 18 factorial times 4 times 3 times 2 times 1. So when I write out 22 times 21 times 20, 19, 18, I can stop at 18, knowing that I'll be able to cancel out the 18 factorials. Multiplying my numerator and dividing by my denominator, we get 7,315 total choices. And we're going to use this number here in a moment. One of the nurses is Erica. Find the probability that Erica will be among the 4 selected. So of the 1 selected, I want one of them to be Erica. So of the 1 selected, I need to choose one that is Erica. But we also need to multiply that by those that are not Erica. So I have 21 nurses left and 3 that are not Erica. And I want to divide that by my total number of options, which is 7,315. We also determined that the choosing of 1 choose 1 is equivalent to 1, so I'm not going to multiply that out. So I need to do 21 choose 3. So that would be 21 factorial. Oops. 21 factorial over 21 minus 3 factorial, 3 factorial. 21 minus 3 is 18 factorial times 3 times 2 times 1. So 21 times 20, 19, and 18 factorial. So that these cancel. So I'm left with taking 21 times 20 times 19 and dividing that by 6, which gives me 1,330 all over 7,315, our total number of options. So multiplying by 1 we know doesn't change anything. So 1330 divided by 7,315 tells me that I have 0.1818. She's got about a 12% chance of getting chosen to be the one. Well, we know that when I add the probability that it will happen plus the probability of it won't happening, it's equivalent to 1. So to find the probability that she will not be selected, we're going to take 1 minus 0.181. So she has an 0.8182 chance, or nearly 82% chance, of not being selected. When shipping diesel engines abroad, it is common to pack 12 engines in one container. Suppose that a company has received complaints from its customers that many of the engines arrive in non-working condition. To help solve this problem, the company decides to make a spot check of containers after loading. The company will test 3 engines from a container at random. If any of these 3 are not working, the container will not be shipped until the engine in it is checked. Suppose a given container has 2 non-working engines. Find the probability that the container will not be shipped. So we're looking for the probability of not shipping. And that's equivalent to the probability of finding 1 defective plus the probability of finding 2 defective. So if I wanted to find the probability of having 1 detected, we have 2 that are not working. We want to find the probability of one of them. And we also have to take into consideration that we have 10 more engines that that hopefully choosing the other 2 will work. This is all over choosing, of the 12, choosing 3. So we also need to add that to 2 of them being defective. So I want to choose, of the 2 that are checked, 2 are defective. And we need to multiply that by, of the 10 that are left, choose 1 that is not defective, because 3 engines are being checked. And then we can divide that by 12, choose 3. So the same probability here. So using our factorial rules, we're going to kind of make this look more complicated before we make it easier. So 2 factorial over 2 minus 1 factorial, 1 factorial, times 10 factorial over 10 minus 2 factorial, 2 factorial, all over 12 factorial over 12 minus 3 factorial, 3 factorial, plus 2 factorial over 2 minus 2 factorial, 2 factorial, times 10 factorial over 10 minus 1 factorial, 1 factorial, over 12 factorial, 12 minus 3 factorial, 3 factorial. And now it's just a matter of multiplying and simplifying. Let's see here. So we're going to end up having 2 factorial, which is 2 times 1, so just 2, over 1 factorial times 1 factorial, which is just 1, times, let's see here, we'll have 10 factorial over 8 factorial, 2 factorial. So 8 factorial, 2 times 1. So when I multiply down my 10, I can stop at 8. 12 minus 3 is 9 factorial, 3 times 2 times 1. So then when I multiply my top, 12 times 11 times 10 times 9 factorial, I can stop. I'm going to just continue simplifying here so we can focus on one at a time. So things that we can simplify down a little bit here. We'll have 10 times 9 is 90, divided by 2 is 45. So 2 times 45 over. And if I multiply 12 times 11 times 10 divided by 6 will give me 220. I'll do my last steps here in a second. All right. Um, 2 factorial cancel out with 2 factorial, and I'm left with 0 factorial, which we know is just 1. On the right here, we'll have 10 minus 1, which is 9 factorial, times 1 doesn't matter, so you can just ignore anything that's 1 factorial. 10 times 9 factorial over, well, we already figured out what 12 factorial over 12 minus 3 factorial was. We decided that that was 220, so over 220. So this is equivalent to, if we just keep going, our 9's cancel. So I'm left with 1 times 10, which is 10. So 10 over 220. And this is equal to, well, 2 times 45 is 90 over 220, plus 10 over 220, which is equivalent to 100 over 220. And if we reduce that down, we'll have 1 over 22. If we took 1 and divided it by 22, we'll get 0.4545. So there's a 45% chance that this particular container won't be shipped. So, in a common form of the card game poker, a hand of 5 cards is dealt to each player from a deck of 52 cards. How many possible hands are there? We don't care what order cards we get in poker. It's how we play the game that really matters. So how many hands are possible? So if I have 52 cards and I want to choose 5 of them, we can use combinations in order to determine how many hands there are. So we'll have 52 factorial over 52 minus 5 factorial, 5 factorial. 52 minus 5 is the same as 47 factorial. So when I multiply down, I can stop at 47 because now I know that those will cancel. So if I were to multiply 52 times 51 times 50 times 49 times 48 and divide it by whatever 5 times 4 times 3 times 2 times 1 is, and you can use your calculator to multiply and divide, you will see that there are 2,598,960 ways in which we can be dealt 5 cards, which is a really ton if anybody plays poker. That's a lot of different options to be given. Let's determine what the probability is of getting a hand containing only hearts. So there are 13 hearts in a deck. So I want to choose, of those 13 hearts, I want to choose 5 of them and multiply it by the probability of not getting a heart. Well, there are 39 cards left and I want to choose 0 of them because I want all of them to be hearts. And then over how many total options we have, which we already know from up above. Alright, so we're going to have 13 factorial over 13 minus 5 factorial, 5 factorial, times, you're going to learn another rule here, 39 factorial over 39 minus 0 factorial, 0 factorial. We know that 0 factorial is just 1. If I have 39 minus 0, I have 39 factorial. So ideally what happens is these just cancel themselves out and I'm left with 1. So anytime you have a number and you want to choose 0, our only option is one of them. And then I'll multiply this by, let's see here, 13 minus 5 is 8 factorial. So 8 factorial, 5 times 4 times 3 times 2 times 1. So 13, 12, 11, 10, 9, 8. So again, I'm relying on you to use your calculator here to help me out and multiply. So if I multiply 13 times 12 times 11 times 10 times 9 and divide that by whatever 5 times 4 times 3 times 2 times 1 is, and we multiply that result by 1, you should get 1287. And when we divide that by the total number of choices we have, the probability of getting a hand that only contains hearts is a very teeny tiny one. When you divide that out, you'll get 0.0004952. So a very tiny likelihood of getting all hearts. What is the probability of a flush of any suit? 5 cards of the same suit. So we just found above here the cards of getting a heart, but we have 4 different suits that we could choose from. So I'm going to take 4 times 0.0004952, and that's going to equal 0.001981. So you have a slightly higher chance of getting 5 cards of any suit versus just getting the 5 cards of just the hearts. let's figure out the probability of a full house of aces and eights. 3 aces and 2 eights is what that means. So I want to choose, of the 4 aces I have, I want to choose 3 of them that are aces and multiply that by, of the 4 eights I have, I want to choose 2 of them to be the ones that I need. So that means if I've already used 4 of my options, I have 44 left that I want to choose no cards from, because I want them all to be aces and eights. And of course we're going to divide this all by 52, choose 5, which we already know what that is. So off to the left here I'm going to do each one of these. We already do know that 44, choose 0 is going to be 1, right? And we're going to divide this all by 2,598,960. So I just need to figure out what 4 choose 3 is and 4 choose 2 is. So let's start with 4 choose 3. So 4 factorial over 4 minus 3. Hopefully by now you're getting the hang of the formula. So 4 minus 3 is 1 factorial, and then we need to multiply that by 3 factorial. So this is the same as 4 times 3 times 2 times 1 over 1 times 3 times 2 times 1. These cancel, so I'm left with 4 divided by 1, which is 4. Now let's do 4 choose 2. So 4 factorial over 4 minus 2 is 2 factorial, and then I have to multiply by that last number in its factorial. So this is equivalent to 4 times 3 times 2 times 1 over 2 times 1, 2 times 1. 4 is the same as 2 times 2, so 3 times 2 divided by 1 is just 6. So when I multiply my tops together, I'll get 24 over 2,598,960. And when I divide, the likelihood of this happening, specifically having 3 aces and 2 eights, is very teeny tiny. Almost not even recognizable, almost having no probability of that happening. Let's determine a full house, but this time we're a little more lenient. We have 3 cards of one value and 2 cards of another, so we don't really care. So we have 13 different options. We have anywhere between an ace to a king. So I have, and each one of those has 4 options within it. So I have 13 options, so 13 ace through king. And of those options, each one has 4, and I want to choose 3 of those 4. Well, now that I've chosen one of the values, we now only have 12 options left. Let's say we have ace through queen left. And each, again, one of those has 4, and we want to choose 2 of those. All over 52 and 5. And thankfully we've done some of this legwork already. So this is equivalent to 13 times, well, we already know that 4 choose 3. 4 choose 3 here was equivalent to 4 times 12 times, and then 4 choose 2 was equivalent to 6. All over 2,598,960. So if I were to multiply 13 times 4 times 12 times 6, we get 3,744 divided by 2,598,960. And if we were to use our calculator and divide, we have a slightly higher chance of obtaining any full house that's out there versus just a specific one that contains aces and eights. All right, 2 pairs. Let's find the probability of getting 2 pairs, one of aces and one the other of kings. So we want 2 aces, 2 kings, and a 5th card that is neither ace nor king. So We have a combination here. We have 4 aces. We want to choose 2 of them. Multiply. 2 kings. We have 4 kings. We want to choose 2 of them. And we have 44 cards left. And we don't care. We just want to choose one of those cards. That's our 5th card. So 2 cards, 4 cards, 5 cards. All divided by 52. Choose 5. Okay, we already know what 4 choose 2 is. Again, 4 choose 2 ended up being 6. So we're going to have 6 times 6. Remember, if anytime you have, if I have 44 cards and I want to choose one of them, I have 44 cards to choose from. So I don't need to use the formula. Divided by 2,598,960. And when I divide, multiply, and divide, we will see that we have 0.0060947 probability that we'll get 2 pairs, specifically 2 pairs, one that's aces and one that is king. So a very tiny percentage of that happening. And this concludes section 8.3, probability applications of counting principles.